Welcome to the 7th lecture, and I hope everybody had a good weekend. So in chapter 3, we started off by looking at characterizing the running times of algorithms. So somebody had asked whether we're only focusing on running time and we're not looking at space. Yes, we will be looking at space as well, but primarily running time is of most interest. But if necessary, space will be looked at as well. And then we looked at the divide and conquer algorithms, and now we're moving on to probability. And unfortunately or fortunately, you can't get away with probability in this course. Okay. So for those of you who are encountering probability for the first time, it might be a little tough. Just try to pay attention, go over the appendix. There's an entire appendix devoted to this in CLRS, and try to get as much help as possible, because probability is an area which is somewhat difficult, and people do get confused a lot of times. And then towards the end, we'll also try to look at something called randomized algorithms, okay, which of course depends on probabilistic analysis. So let's go forward. And in the last lecture, we started off, and just towards the end of the last lecture, I think in the last 5 minutes, we were looking at the following slide, which was a review of probability, sample space, and outcomes. Okay, so we looked at 2 examples of experiments. So the first experiment comprised of rolling a single die, and the outcomes were defined as the outcomes of a die, which are 1 to 6, and the sample space was a set of all possible outcomes, which was 1 through 6. And the second example was tossing 2 coins. Okay, so that's a single experiment, but it comprises of tossing 2 coins. Okay, and so that experiment generated the set of possible outcomes as to be H, and all the way up to TT, the 4 possible outcomes. Okay, now notice that we said that these outcomes are mutually exclusive. Okay, so that should be clear. And then we also defined probability on each one of these outcomes, and we said, well, if you look at the entire space, then the probability over all possible outcomes has to be naturally equal to 1. So hopefully all of this is fairly straightforward. And now let's take a look at some further concepts. So can somebody tell me what they understand from events? Okay, so we've talked about outcomes. And for those of you who are already familiar with probability, should remember what an event is. And how is that different from an outcome? Outcome versus events. There's a difference, right? What is that difference? Somebody should remember. Is an event an outcome? Just another word for an outcome? No? No? And what is it? You'll have to speak up, Carl. Just, yeah.
All events can be an outcome.
Only, say that again, only the last part.
One event.
Only one event can be an outcome. Okay. All right. Not exactly what I'm looking for. Somebody else, give it a shot. What's the difference between an outcome? So as I said, an outcome is one result of an experiment. Okay. Could be, and what, so an event is different. Okay, just a hint. Yes. Again, you guys have to speak up. I'm sorry. I might be, you know. All right. No. So outcome is not a series of that you're expecting. Outcome could be just one of those results. Okay. So if you roll a die 1,000,000 times, it's the number 6 million. Right? You roll it 10 times or 100 times, so, but it is possible. All right, so the outcomes are 1 through 6. Those can come out, right? So people are still not clear what an event is, despite having gone through a probability course. Okay, so let me jog your memory. So an event is actually a subset of the outcomes. Okay, you have to make sure that your basics are right. So the event is a subset of the outcomes. Okay, I'm not sure, Kyle, if that was what you were getting at, but there's a difference between, I think, what you were saying and what I'm saying. So the outcomes are, if you're rolling a die, it's 1 through 6, and then you can define an event. You can define a whole bunch of events. Okay, so one event could be an event A, which is one subset, which could be, let's say, 1, 2, 3, 4. You could define a different event, which is B, which is 4 and 5. Okay. Now I said the outcomes are mutually exclusive, right? But are the events mutually exclusive? Yes.
Not necessarily.
Not-
You have to say that, like here, you have event.
Yeah. Exactly. So events don't necessarily have to be mutually exclusive. They could be, but they don't have to be. Depends on how you define it. So in this particular case, clearly you can see that one of the outcomes is actually common between the two events. Okay. Next, let's try to define probabilities. So we already saw probabilities on the outcomes, right? So we said that each one of these outcomes has a certain probability and these are mutually exclusive. But now similarly, you can define probabilities on events as well. Okay. So let's define probabilities on the events A and B, and we'll also try to use a Venn diagram. Hopefully you've seen that before. So so how would you define the probability of A? And somebody tell me what these probabilities are. And perhaps you can also venture to guess what the intersection of A and B is and what is the union of B. So I'm looking for a whole bunch of answers. Shouldn't be too difficult. Yes.
Probability of A, B, state.
Okay.
B, state.
Yeah.
Intersection.
Yes. Does everybody see how we're getting that? Okay, hopefully fairly straightforward by now. Okay, so we're simply saying, well, these are the possible outcomes, and I've plotted and I've shown them in this space. This is the entire space shown as Venn diagram, and I've simply shown the 4 is an intersection. So this is event A, this is event B, and there is one outcome which is in common, and that is why the intersection is 1/6, which is simply the probability that the outcome 4 comes in, and so on. So you can see all of this. So probability of A is 4.6, probability of B is 2.6, and this is assuming that each one of these outcomes is equally probable, right? And one more thing that you notice that we can also define probability of A union B as the probability of A, okay, which is all of this, plus the probability of B, which is all of this. But then, since one of them is common, you have to subtract that. Okay, so you might subtract the intersection. Okay, so hopefully all of this should not be too difficult to understand. So, so those were events, and now we've defined probabilities on events. We've also been able to define what are intersections, the unions of events, and so on. Okay. Now, how do we define mutually exclusive? Okay, so I'll just go ahead and define this. So mutually exclusive events are those in which the intersection is 0. Okay, so if you can just look at the previous example, as you've already seen that these are not mutually exclusive. A and B are not mutually exclusive because the intersection does exist. Okay, so if you can think of mutually exclusive events where the intersection is 0, then those are defined as mutually exclusive. So just give me some examples of mutually exclusive. For example, if you're throwing a single die, what can you define A and B? Yes. Okay, very good. So all the even and odd, and clearly you can see that there is no intersection. Okay, so let's look at a different example. So I've defined A as 1, 2, 3, and defined B as 4, 5. So you can see that none of the outcomes are common between these two events. And so they are mutually exclusive. Okay. A intersection B is 0. And as you can see, property of A union B can be now be simply the sum of these two. Okay, so far so good. So let's think about conditional probability. All right, so what do people understand by conditional probability? All right, so this over here. So conditional probability can be denoted as the following. So probability of A given B. Okay, so what is the probability that event A has occurred given that in the same experiment you already know somehow that another event has already happened. So we already know that B has already taken place in the same experiment. And now we want to know what is the probability of A. Okay, so probability of A given that B has already occurred. Okay, so let's say we look at this example. We say, well, the same example, we've thrown a single die. And we know that, let's say, probability that B has actually occurred. Okay, so B has already occurred, which means that the outcome is either 4 or 5. Okay, so how would you calculate probability of A given B? Now, B has occurred, and now we want to find out what is the probability that A has also occurred. How would you calculate that? Yes?
The intersection of probability of A.
Okay, very good. And what does that come out to? So it comes out to be probability of intersection B is 1/6, and probability of B is 2/6, and that comes out to be 1/2. Right? So basically what we're saying is that we're given that the results are either 4 or 5, okay? And now what we want to know, what is the probability that event A has also occurred? And the only way that A could have also occurred is that if it was actually 4 and not 5. Okay, and so it's either 4 or 5, and the probability of 4 having occurred, given that 4 or 5 have occurred, is simply one of the two. Okay, so that's half. What about probability of B given A? Okay, so if you can use the same example to figure this out. So how would we write this? Now we're saying that A has already occurred. So let me delete this. Now we're saying that A has occurred, which means that the result is either 1, 2, 3, or 4. And now what we want to know is what is the probability that B has also occurred? So clearly, that could only be possible if 4 again was the number that was given that 1, 2, 3, or 4 had occurred. Okay, so clearly from intuition, you should be able to say, well, what should that be? What's the probability that 4 occurred, given that 1, 2, 3, or 4 have occurred? 1/4. Okay, so that's 1/4. All right. And how did we get that? Well, again, we use the example, the equation that the gentleman gave earlier is that we look at the intersection of probability of A given B, A and B divided by not the probability of A this time, not the probability of B this time, but the probability of A. Okay, so the intersection divided by the probability of A. Okay, so far so good. So so this is what you get that we just worked on, and let's go forward. Now there's also a chain rule, and we can define this as follows: that if you have two events which are not independent, okay, in other words, A intersection B is not 0. So for non-independent events A and B, what you can say is that probability of A given B is simply probability of A intersection B divided by B. We already know this, okay? This sort of came out from our previous example. And now you can simply cross multiply and you can say, well, we can express probability of the intersection of these two by taking probability of B on the other side And we can express the intersection as simply the conditional probability of A given B multiplied by the probability of B. Okay, so we've simply taken our earlier definition and we have done some cross multiplication. Okay, and you can also express that as probability of B given A times probability of A. Okay, so you can see that from the previous two expressions, we can have probability of A given B and probability of B given A. And if you cross multiply this, okay, we have two different expressions for the intersection of A and B. Okay, one of them is probability of A given B multiplied by B, all right, or probability of B given A multiplied by probability of A. So two different ways of expressing the intersection. Okay, and so if we just use the short notation A comma B comma C to imply the intersection of all three, then you can also generalize this to say that probability of A, B, and C, the intersection of all of these is simply the probability of A given B and C multiplied by probability of B and C. Okay, and then we this is why it's called a chain rule. We can sort of keep expanding, and so we can express something in this form: probability that the intersection of A, B, and C events is simply A given B and C multiplied by B and C multiplied by A given B and C multiplied by the probability of B given C multiplied by probability of C. Okay, and this could be written in different ways. So you could say probability of C given A comma B, all right, multiplied by, and you could express that in different ways. Okay, so this comes in handy once in a while. So it's useful to know this chain rule. Now, we spoke about mutually exclusive events, but there's a different type of events which are called independent events. Okay. Now, can somebody tell me what's the difference? Are these again two different names for the same concept, or do they mean something different? Yes. Okay. Okay. Very good. Sorry. Okay, very good. So that's one definition, and it's perfectly fine. So in other words, if A and B are independent, if probability of A does not have any effect on probability of B, and vice versa. Okay, so we're saying that these are two independent events. So I mean, think about in everyday lives, you could have two completely different things happening in two different classrooms, and you'll say, well, they're not related. Okay, the probability, the fact that something happened over here versus something happening in a different classroom, these are independent, okay? But they could both happen. So if you're saying that these are independent and they don't interact with each other, then given that we know that B has occurred, how could you express the property of A given that B has occurred as a simpler version? Yeah. Okay. So does everybody see that? That given that they are independent, then the fact that B has occurred does not have any impact on A. Okay, just by the intuitive understanding of independence, that should come out. Okay, and vice versa, probability of B given A should simply be probability of B. Okay, so does that all make sense? That goes along what you just defined earlier. So so if you know this, that you can, if you have a conditional probability and if they are independent, then the conditional probability simply boils down to a given probability. Okay, and B can simply be neglected if B is independent of A, and vice versa. Okay, so if that is the case, then how can we write this? So we've already got this notation. Okay, so we already seen that probability of A given B can be written as probability of A intersection of B divided by probability of B. So if these two are independent, then what does the intersection equation become? Okay, so how can we write this? Okay, so how would we write the probability if A and B are independent? then the intersection can be represented by what? Just take a look at what something we've already seen and do some cross multiplication. So what's the intersection of property of A and B? We want to know what's the property that both of these events have happened, given that they're independent. Yes. Okay, very good. So it should simply be property of A times the property of B. Well, it's coming out right from this equation. So we've already seen that A intersection B is property of A given B times the property of B. Okay. And since these two are independent, that comes out to be property of A, and that comes to be property of B. So you can see that whenever you have two independent events, then to be able to say, well, both of the what is the probability that both of them have occurred? All you need to do is independently find out what's the probability that one event occurred and what's the probability of the other event occurred, and you simply multiply them. Okay. So things become simple if you have independent events. But that's not how life is. A lot of cases you have a lot of events which are mutually dependent on each other. Okay. So actually the definition, and this is actually the definition, is that if you want to say, well, you want to check if these two are independent, what you could do is use this equation to be able to say, well, this is the left-hand side, the right-hand side, and are these two equal? If they are equal, then by definition, these two events are mutually are independent, not mutually exclusive, but they are independent. Okay. So let's take a look at a few examples of these. So let's say again, we go to our favorite example of throwing a single die. Okay. And I've got A is equal to 1, 2, 3, 4, and B is equal to 4 and 5. Are these independent? Okay, so how do we check independence? We will say, well, what's the probability of A intersection B, and can that be written as a product of these two? Okay, so let's do that. What's A intersection B? Well, that's clearly 1/6. And this A is 4/6, right? And B is 2/6. And if we calculate that, that comes out to be 1/6 and 2/9. Okay, so from our definition, we can simply do the calculation and say, well, they are not independent. Okay, and you could have sort of guessed that they're not independent simply because, you know, the fact that B has occurred does seem to have an intuitive impact on the property of A. Okay, so instead of property of A being 4/6, it becomes 1/4. Okay, and the property that A has occurred has an impact on B because they have some intersection. One of the outcomes is in common, right? So let's take a look at another example. I've defined A as 1, 2, and 3, and B as 3 and 4. And now, can somebody do the math for me? And tell me what is the answer? Just do it intuitively in your head and tell me. And also give me an intuition. Are these two independent or not? Is A, what does your intuition say? What does the math say? Is it all making sense? Yeah. These are not independent. Okay, so can I get your name? Logan. Okay, so Logan says that not independent, independent, and not independent. Okay, so Logan. Who else? And that's from intuition or from the math? Okay, so from the intuition, you're saying that they are not independent. Okay, anybody else? Yes. Gentleman over there. Your intuition says they're independent, and can I get your name? David. Okay, so we have David, Logan. All right, who else? And again, is that from intuition or from the math? Okay, everybody's doing the intuition. That's good because you need to develop some kind of intuition as well. And can you explain your intuition? Why, David, why do you think that they are independent. You have to speak louder and okay, wait a second. So you confuse, so hold on a second. You're confusing multiple throws of the die. No, don't get confused. This was a single experiment, and now the experiment is done. We're not doing any further experiments. We're not throwing a die multiple times. Just thrown once, and we have the result now, but we don't know what the result is. Okay, it's behind. It's somebody else is seeing it. We don't see it. Okay. Now that other gentleman or lady is saying that can tell you partially the information. They can tell you, well, has A occurred, or they can tell you has B occurred. And now you're trying to figure out, well, that experiment has happened. We don't know the results, but this person is telling me what the results are. And this person is saying, well, A has occurred, or they can tell us B has occurred. And now we're trying to find out whether are they independent or not. The fact that you know that B has occurred, should that influence the probability that A has occurred? Just knowing that B has occurred, let's say that we know that 3 and 4 have occurred. Does that change the probability of A occurring? So people are nodding. Somebody else, yes.
And then we know that we're in set for probability for we have 3 rather than 4 is also.
Okay, right.
Therefore, the probability of A.
Excellent. Can I get your name? Jack. Okay. So Jack is also agreeing. And I think now, as compared to David, I think you were thinking perhaps along multiple experiments. And you can see Jack's analysis, where he's basically said, well, if you look at the Venn diagram and you're saying, well, the fact that B has occurred, well, if you just look at A, the probability of A occurring is half, right? It's 1, 2, 3 out of 4, 5, and 6. And now somebody's telling us that B has occurred. Now we want to find out what the probability of A is. Now, B is equally straddling between A and A naught, okay, and not A. Why? Because, this is a half, and the probability that B has occurred is equally straddling that. It's on both sides. And the fact that B has occurred now actually is not really telling us anything about the probability of A, right? Simply because of the way the problem is structured. It just happens to be in such a way that B is straddling on both sides, okay? 1, 2, 3, 4, 5, 6, and B is on both sides equally. So probability of B, the fact that B has occurred should not impact the probability of A, which is sort of telling us that Jack's intuition is correct. I don't know if anybody else, and Logan's intuition was not correct. Okay, so where is Logan, by the way? Yeah, can you think back now? Can you agree with Jack, or do you think that you are still feel that it's not independent? Okay, so now you can see why Jack's analysis makes a lot of sense. All right, so let's do the math now and see if the math is also is making sense. So you can see that probability of A intersection B is 1/6. Okay, and if you do the right hand side, the probability of A is 3/6, probability of B is 2/6, and the numbers match. Okay, so our intuition is confirmed by the math. Okay, that you can. So if you have a complex problem and your intuition is not really giving you the right answer, well, then you can simply do the math and figure out whether the left-hand side is equal to the right-hand side in this equation. Okay, so so that is an example of independent events, and as I said, independent events and mutually exclusive events can become confusing at times. So you need to understand some other examples. Maybe let's take a look at a third example. So here you have what A is defined as 1, 2, 3, and B is 4 and 5. Okay, in other words, clearly they're mutually exclusive. Okay, so should mutually exclusive events be independent? No, who said no? Yeah,
If one of the events happens, there's a one.
yeah. Yeah, so clearly the fact that one of the events has happened, it sort of implies that now 1, 2, 3 has happened. Okay, so clearly B couldn't have happened because they're mutually exclusive. So clearly the intersection is going to be 0, and so the left hand side is going to be 0 for mutually exclusive events, and the right hand side is clearly not 0. Okay, it's some 3.6 times 2.6. So 1/6 is not equal to 0. So for mutually exclusive events, they're never independent. Okay. Let's take a look at yet another example. Okay, so this is now to clarify multiple experiments. Okay, so now you're doing an experiment in which you're throwing 2 dice. Okay, and we're defining A as the event 1, 2, 3 of die number 1. Okay, and we're defining A such that it doesn't really matter what the second die has. Okay, so A is only defined on the first die, and B is only defined on the outcome of the second die. Okay, so it's the same experiment. You've thrown 2 dice, okay, or die, and you're defining event A as 1, 2, 3, the outcomes of either 1, 2, or 3 of the first die. You don't really care about the second one. And B is defined as event of some set of outcomes on the second die. Okay, so are they now independent or not? So what does your intuition say? Yes. Yeah, so you even though it's a single experiment, but you've thrown unless they are tied in by quantum effect, okay, which does happen sometimes. Assuming that there is no quantum effect between those 2 dies, they're independently being rolled, and so just by definition, you should be able to see that they are independent. Okay, and the probability intersection and the left hand side and the right hand side can be matched as well, because this is simply the property of 3.6 times 2.6, and it's sort of quite obvious that these are independent. Okay. All right. So independent events, mutually exclusive events, hopefully that is somewhat clear. Now let's go on and take a look at another concept. So there's a law of total probability. Okay. And basically what it says, if that B sub I are mutually exclusive events. Okay, so for example, B and B naught or B bar are mutually exclusive. Okay, A bar, they're mutually exclusive. Or if you can think of the 6 outcomes, right? Those 6 separate outcomes, they're all mutually exclusive. Okay, and they're also exhaustive. In other words, 1, 2, 3, 4, 5, 6, they cover the entire space, sample space. A and A bar, it also covers the entire sample space. Okay. Then what you can do is you can write one probability as follows. So you can write probability of A as the probability that of A given B times probability of B plus the probability of A given B didn't occur times the probability of B not occurring. Okay. So just think about this, and hopefully you can sort of make an intuitive sense of why this is true. Okay, so basically saying, what is the probability that an event A has occurred? Okay, now we're saying that some other event, which may or may not be independent. Okay, now we're trying to relate it to that, and we're saying, well, there are 2 probabilities. There's a probability that B occurred, and there's a probability that B didn't occur. Okay, and these 2 are mutually exclusive. Okay, so what we can do is we can have a weighted sum of probability of A, And we can say, well, we're going to say the conditional probability of A, given that B occurred, I'm going to weight it with the probability of B. And the conditional probability that B did not occur, the probability of A, given that B did not occur, I'm going to weigh that with the probability that B did not occur. Okay. So if you don't completely get that, just look at it, and hopefully that should make sense after a while. Why is this important? Because this leads us to a very important equation, which is extremely useful and comes in very handy, perhaps not in this course as much as in AI. Okay, so AI is full of Bayes' theorem, and if you've taken AI courses, you'll have seen Bayes' theorem being referred to. Okay. So Bayes' theorem basically says is I'm going to use this equation, okay, to define a particular probability as a weighted sum of another event. We can just use a little bit of math and combining things that we already know. What's the conditional probability? Is the intersection probability divided by the probability of B. And so this intersection can be represented by the chain rule. Okay, and so now there's another way of writing the chain rule. And if you think about this, it seems to be like almost a trivial, manipulation of the earlier equations. Okay, and it has a whole theorem named after some gentleman called Bayes, right now, and it's extensively used. And you wonder sometimes why, people get so famous just by manipulating a few equations which are already kind of obvious. But this has a lot of implications. Okay, this particular way of representing the conditional probability becomes extremely useful, not just in AI, but actually in a lot of practical problems. Okay, so in a lot of practical daily real-world problems, Bayes' theorem becomes extremely relevant. Okay, and in fact, I used to tell my students that I use Bayes' theorem in actually grading them. Okay, why? But that's another story. But let's take a look at a few examples, maybe at least one example of how Bayes' theorem can come in handy. Okay, so let's take a look at a particular example. So let's say that you observe one of your colleagues. Okay, he or she is a UNC student, and that person knows a lot about technology. Okay, so he's what you might refer to as a techie. Okay, so now you know that the majority of UNC students are not computer science majors. Okay, you guys are a minority, obviously. There's a whole bunch of other majors, but you also know that computer science majors are generally techies, right? So there's probably going to be very few computer science majors who don't know about technology. Maybe they're a misfit or something. Right? But generally speaking, computer science majors, would know a lot about technology. It might be classified as techie, but not all of them. Right? There'll be some exceptions. People who are in there for money. Okay. So the question is, if somebody tells you you found a student. He seems to be, you don't know if he or she is a computer science major. All you can see is just by speaking to them is that they know a lot about technology, right? So now you go back and you're wondering, is that person, you think that person that I just spoke to, was he or she a computer science major or not? Okay, you try to, you go in the evening and you're trying to use Bayes' theorem and you're trying to figure out, can I use Bayes' theorem to figure this out? Okay. So first of all, again, your intuition. How many people think that they are more likely? Okay, so more likely to be a CS student versus a non-CS student. So this is what we're basically saying. What is the probability that the person is a CS student, given that he knows a lot about technology or she, versus what is the probability that they are not a CS student, given that they know a lot about technology. So we're given that they know a lot about technology. We're just trying to figure out what are the odds. Okay. So what does your intuition say? Is that person a CS student likely, or is this more likely? More likely or likely? Which one is it? Yes. Okay, can I get your name? Rishi, okay. So Rishi is suggesting that from his intuition that, just the fact that, computer science majors know a lot about technology, the chances are that the person will know a lot about technology. Okay, and so he's going to be his computer science major. Anybody else who has some intuition about this? Yes. Okay, so Kyle is suggesting that it's more likely to be the person to be a non-CS major because you take into fact the fact that that person was a UNC student. Okay, and we know that the majority of students on campus are non-CS majors. Okay, and you're just a very small percentage of the whole population. All right. And so that a priori fact is sort of telling you that, well, wait a second, even though, 90% of the computer science majors may be techies, but the fact that even if half of the other guys are techies, or even 1/3 or 1/4 of them are techies, okay, in this age, almost everybody knows about technology, but just the fact that their numbers are so large as compared to the computer science majors, that should impact the overall probability. Okay, and that's where Carl's intuition is saying is that that it's more likely that the person is a non-computer science student. Now, somebody else had actually their hand up behind you that I was pointing to. Do they want to respond? Does anybody else want to go either way? Rishi versus Kyle. How are we doing? You guys right next to each other. Okay. Anybody would want to make give a vote in favor of either one of them? Could you have a vote? How many of people think that is going to be? How many of people think they actually think that it's going to be Kyle? And how many of you think that it's Rishi? Phew, Rishi, you're not going to win a vote over here. So you think, and would you like to explain why you think it's going to be more likely that is it the same reasoning? Okay. Well, the majority in this case is actually correct. Doesn't happen all the time, but the majority is correct. Okay. So let's take a look at, and let's try to come up with actual numbers. Okay. But a lot depends on the actual numbers. So we're making assumptions. And we sort of, throwing darts in the dark room. So in order to be absolutely sure, we have to actually try to work it out. Okay, it's not good enough to actually just work in the dark. So the Bayes theorem is basically going to say, well, we can express this. If you look at the early equation, we can express the probability B, given that you have B. We can find out what is the probability of A in the following way. Well, it says that now we can reverse the equation and we can say, well, what is the probability of B given A? In other words, what is the probability that somebody is, so in this case, A is computer science, okay, and B is technology. So now what we're saying is, what is the probability that a CS, given that somebody is a CS major, what is the probability that they are techies? And that maybe we can estimate. Okay. Similarly, what is the probability of A and the probability of B? Okay, so the probability of A is essentially how many CS students do you have? Okay, in the entire population. So if let's say you have 1,000 students who are computer science majors and the campus has a total of 5,000, then probability of A is fairly clear. Okay. Now, what is the probability of somebody being a techie? That's not clear. So how do we express probability of B? So probability of A, I said, is easy just by looking at the numbers of how many people are in the CS major. We can guess this. So we can say, well, if you are a CS major, the likelihood is you could just look at within your own class and you could say, well, how many of you guys, how many of your friends are techies? Okay, and let's say your computer science friends, okay? And you can make a guess of this and you could say maybe 90% or 80%. Okay, and this could be, let's say, 1/4 or 1/5. Now, the tricky part is how do we actually determine probability of B? So how do you determine what is the probability that somebody on campus knows about technology? That doesn't seem to be kind of obvious, right? So how do we solve that problem? Is there something that I just looked at in a few slides ago that could help us? We said that you could determine the probability of an event as what? Just a couple of slides back. I'm not going to show it. Think. We said that you could take an event and you could break it down in terms of another event, but that other event would be, you have to break that other event into mutually exclusive events. Okay, so let me show you what I spoke about. So this was the equation. Okay. So we said that we could take probability of A and express it as in terms of another probability. And let's say we have the other probability is B. We could express it as a weighted sum of the other event, but break it up into mutually exclusive events. Okay, and then we could express it as conditional probabilities. Okay, so that's sort of a clue as to how we could actually figure out what is the probability of somebody being a techie on campus. Okay, and so let's take a look at how that could be done. Okay, so we could say, well, probability that somebody is a techie on campus is a weighted sum of somebody being a probability of being a CS student and a non-CS student. So these are hopefully fairly obvious just by looking at the numbers. And then we could say, what is the conditional probability? Well, given that you are a CS student, we estimated that, it's very high, let's say 90%. Okay, you know that your friends are all techies. But what is the probability that a non-CS student is also a techie? All right, you'd have to go outside your comfort zone and mix with the students who are not some computer science majors and find out, well, I know these 5 people who are non-computer science majors, and I know that 2 of them were techies and 3 of them had absolutely no clue how to operate a computer. So, so you could estimate this. This would probably not be so high. It might be, 2 upon 5 or some small number. It would be relatively small as compared to computer science majors. Okay, so all of these numbers you can actually estimate. Okay, so you can see where we're going with this. You can actually take a real world problem and given enough time and interest, you could actually break it up into other events and sort of try to come up with a real number. Okay, so here's a Venn diagram, and I've just come up with some numbers over here. Okay, so let's take a look at my guesses. So what I'm saying is that, let's say that, as I said, the probability that a computer science major is a techie is 90%. Okay, and we're saying that the probability that a non-computer science major is a techie is a lot lower. Let's say 30%. Okay, let's say you have a total of 5,000 students on campus, just a random number, and 1,000 of those are computer science majors. So you know that this is 20% of the students are computer science majors. And 80% naturally are non-computer science majors. Okay, so we've got all those numbers. Okay, and then we can plug those numbers in and we can now figure out. So I've sort of shown it over here. This is the Venn diagram. This is all the 4,000 non-CS majors. Okay, these are the 1,000 CS majors. We're saying that 90% of these are techies. Okay, and only 30% of these are techies. But what do you notice? Kyle's intuition was coming out right, okay? Simply because of the fact that this is such a larger group, even 1/3 of them being techies, that number becomes really large, okay? And that number is actually larger than this number, okay? So if you do the math, this is coming out to be 30% of 4,000, 1,200 students, and 90% of a much smaller set, which is coming out to be 900 students. So 900 divided by 900. So now you have to divide it over this portion. Okay. So we're basically saying, what's the probability that this particular shaded area has occurred, given that we know that this or this have occurred. Okay, so it's 900 over 900 plus 1200, that is comes out to be 43%. Okay, so in this example, it's not the perfect example. The numbers are close to 50%, but as you can see, if you actually applied it to your scenario, it might actually come out to be a lot smaller, simply because I think these numbers are not very accurate. It would probably be more like 1,000 students out of maybe 20,000, 50,000. I don't know what the numbers are. So this actually might be a lot smaller. So as you can see that the probability that's a CS student comes out to be a lot smaller. Yeah.
This example, how do you calculate probability?
Okay. So I didn't actually show it. Okay, but I just did the intuitive way. But you could actually do it. Okay, so what you could do is you could take the probability of techies, which is 0.9 times 1/5 plus this was coming out to be 30%. Okay, times the probability. This is 4/5, and you could calculate this. All right, somebody has a calculator, they could do it. But I just showed you in terms of the actual numbers. Okay, because sometimes it's actually useful to think about it in terms of the actual numbers. So you're talking about where's the probability that was one of these 900 students, given that there is a 1,200 students in the other side as well. So clearly the probability is 900 divided by 900 plus 1,200. Okay, so you're looking at the probability that it's one of these students compared to the population of techies. Okay. So that was one example, and hopefully that you can see that a lot of real world problems are based on Bayes' theorem. Okay, and this is used. I mean, I don't have time, but if this was an AI course, I would give you a lot more examples of where in real life it could be in a lot of legal situations. Okay, so if any of you have been a jury, been part of a jury, you know, in those situations it comes out really handy, right? Because you're just about to convict somebody, but you don't know Bayes' theorem. So I can give you examples where Bayes' theorem would be extremely useful in being able to determine whether somebody is guilty or not. Okay, and a whole bunch of scenarios, but that'll require more time. So let's go on. Now let's talk about what is a random variable. So we've spoken about outcomes. We know what events are. And now what is a random variable? So all three seem to be jogging your memory, but are those all, you know, so you've seen the difference between an event and an outcome, right? So event is a bunch of outcomes. But now what is a random variable? It's just another name for all of that, for an event. What is a random variable? No clue? Somebody must know. Okay, so a random variable is actually a function. Okay, so it's a function that you can define, and it's defined on the outcomes. Okay, so let's say you define the following random variable x. Okay, it's simply the sum of the two dice. So you did an experiment which comprised of throwing two die. Okay, and the possible outcomes, the sample space was 1, 1 all the way up to 6, 6. Okay, and so there's a total of 36 possible outcomes. This is a little different experiment. Okay, and now what we're saying is that we're taking the sum of those two die. Okay, so we're defining a function. Okay, it could be a multiplication, it could be, you know, any other function. All right, as long as you have a function, you can, if you define a proper function, then that would be called a random variable. Okay, so x is now a random variable which has been defined as a function on the possible outcomes, and now we talk about the domain of x. Okay, so the domain of x is all the possible values. Okay, so clearly, because it's a sum of the two die, the least could be 1 plus 1, which is 2, and the maximum could be 6 plus 6, could be 12. And so this is the domain of X. That's how it's defined. All right. And then there's things like probability density function, which you might remember, something very common, probability mass function. So probability density function is generally defined on continuous random variables, but we primarily talking about discrete random variables because the outcomes are countable and they're discrete. Okay. So generally we're going to be talking about discrete random variables in this course. And so we're not going to be talking about probability density function. We'll refer to this as probability mass function. Okay, that simply says what is the probability that that particular event happened. Okay, or that the probability that that random variable took on that particular value. Okay, more accurately. So that's what a random variable is. Okay, here is, so this was one example. Here is another example of a random variable. It's called an indicator random variable, and this comes in quite handy. An indicator random variable can be defined on an event. Okay, so you're defining it an event on A by using the following notation. Okay, if it was an event on B, you could use this notation, and IA is now the random variable, which is a function. Okay, and it simply has two values. It can have a value of 1, or it can have a value of 0. Okay, it's like a Boolean. And it has a value of 1 if the event A occurs. Okay, and it has a value of 0 if event A does not occur as a result of that experiment. Okay. So fairly straightforward. You can go back to the examples that we spoke about, and you can see that you can define an indicator random variable on essentially all the events. Okay, so if, for example, I would say that if we looked at the event A, for example, being 1, 2, 3 out of the possible outcomes, you could define IA to be 1 and 0 again. Okay, so so that's a random variable. Now you need to, of course, have an associated value for the probability of that random variable having different values. Okay, and that's sort of given by the probability mass function. So in this case, for example, if you look at this and analyze this, and you do a little bit of work. So for example, the probability that the random variable X has value of 2, we've defined an indicator random variable. And now let's take what we've learned about the basics of probability. So all of this was hopefully sort of covering very briefly the different topics in probability theory. And now let's try to apply it to some little bit more complex examples. Okay. So we're going to now take a particular problem, and which is given in a fair amount of detail in your book. And this is what is referred to as the hiring problem. Okay. So we're going to apply some of the concepts that we've learned and try to see if we can solve this problem. So here's the following scenario. Okay. You are using an employment agency to hire an assistant. Okay. And the agency has total of N candidates. Okay. And sends you one candidate every day. Okay. You interview that particular candidate, and you immediately have to decide whether that person is good or bad. And basically you compare it to previous hires. Okay. So you must immediately decide whether or not to hire that person. But if you hire, you must also fire your current office assistant, even if it's somebody who you recently hired. Okay. Doesn't seem to be very nice, but that's how the problem is defined. Okay. And I've sort of slightly simplified the problem as given in the book, because the net example is still completely relevant. So let's assume that the cost to hire is C per candidate. Okay. And you eventually need to interview all N of those candidates. All right. And let's say X is the number that you're going to actually hire. Okay, so you're doing a whole series of hiring and firings, right? So you interview the first person because that's the first person you're going to hire that person. Okay, because you don't have anybody else to fire. Second person, you're going to say, well, is this person better or worse than the guy I hired yesterday? Okay. If he or she is better, then you're going to fire the previous guy, unfortunately, and you're going to hire this new person. Okay. On the third day, you're going to have yet another person coming in. And then you're going to compare it to the person who is currently working for you. Okay. Again, that comparison, you might say, well, that doesn't seem to be the best way of hiring somebody. Why don't you just interview all of them at the same time and then decide to pick the best person? Okay. But there is some advantage to this because sometimes you actually want to figure out whether that person did well in the interview, but he or she does he actually perform on the job? Okay, so you give them 1 day or 1 month to perform, and now you have some way to compare. Okay, but then you're comparing it with a simple interview. So anyway, this sort of a rigged problem and is an academic problem. Okay, nobody actually hires this way. But let's assume that this is the problem, and we try to find out what is the total cost of hiring. Okay. Now, whenever you hire somebody, it has a fair amount of cost impact. Simply because you can imagine every time you hire somebody, there's the HR department, and the HR department does a lot of work, as you know, and that whole process of hiring and getting that person an office space and so on. So we try to estimate, we try to minimize the total cost of hiring. Okay, so you can imagine that the best case could be when the first person that you actually hired is the best person. And then you only hire one person, right? Because everybody else who came in subsequently was actually worse than the person you hired. Okay. The worst case could be what? What would be the maximum cost? Yes. Yeah. So in other words, you've been given a sequence of people, and it's absolutely in the reverse way. Okay. So you get the worst person first, then a slightly better person, then a slightly better, and so on. And you get the best person right at the end. Okay. So that's a way that the employment agency will make a lot of money, because generally, they get the first month's salary of the person. So that, unfortunately, could be the worst scenario. Okay. So now you're assuming that if it's a fair employment agency, that they will hopefully give you the results. Well, actually, if they were smart, they were good, they would actually give you the first scenario, right? That they gave you the best person first, and then you could interview the rest of the guys, but you just do one hire. But if they're really trying to make money out of you, they'll probably do it in the reverse order. Okay. Now, the question is, we're trying to estimate the total cost of hires. Okay. And the question is, how do we do it? So any thoughts? How would we convert this into a problem that you can solve? And so it's not a very difficult problem, intuitively speaking. Okay, but it does require some analysis, some thinking about it. And the problem itself can be converted, can be changed as well. Okay, so let's think about that. We've been talking about randomized problems, right? We've referred to a probabilistic analysis versus a randomized problem. Okay, so here is where that illustrates the difference. So in the first scenario, let's say that the employment agency is giving you the people, and now you're doing a probabilistic analysis, and you're going to make some assumptions about the order in which the agency gave you those candidates. Okay. Now that's a big assumption, and as you said, it's possible that the agency is actually trying to make maximize their own profit, and they actually don't give you the candidates in a random order. They actually pre-sort it, and they give it to you in the reverse order. Okay, so that's going to maximize. That's going to make you the worst situation. You're going to have a very high expense. And if it was good agency, maybe they're doing it the first way, right? They're already sort of giving you the best candidate. But let's assume that they're doing it in completely random order. But there's a big assumption, okay? And a lot of times you can't really rely on that assumption when you're trying to create algorithms, okay? So what could we do? how could you change the problem so that the results are somewhat more, you can actually predict the results a little better. What could you do to change the way this whole setup is being run, so that you can actually have a much more accurate estimate of the expected cost? Yes. So you could completely change the problem, and you could say, well, we're going to interview all the candidates together. Sorry, say that again. You're going to size a certain number, decide how many of them are you going to interview? Is that what you're saying? So let's say if you have 100 candidates, you change the problem to say, well, I'm going to interview maybe in lots of 20 or something like that, or you just interview a subset of them. How are you changing the problem? I'm not quite exactly getting you. Okay, so yeah, so that could be one way, is that you interview the first person, and then this subsequent set you interview maybe a bunch of them together, and then you decide. I don't know if I'm completely understanding the way you phrased it, but yeah, you could change the problem that way. But let's limit the ways in which you could change the problem. Okay, so one of the ways that we're not going to change the problem is completely change the mechanism. Okay, so we're still going to interview them one at a time. Okay, and we're still going to interview and we're still going to hire and fire the way we've defined it. Okay, so there are some constraints. Okay, but think about the general direction in which I'm going. I'm trying to convert this into a randomized. That's what should be sort of a hint. I'm trying to convert this into a randomized problem. Okay, so I get what you're saying, but I'm not completely opening up the problem. Okay, I'm trying to modify it in a limited set of way. And I'm trying to say, well, can I convert it in a simple way so that I can actually give a reasonable idea about what the expected cost would be. Okay, so I don't know if I'm getting, if you, okay, you get it. Okay, yeah. So somebody else, yeah. Okay, so if we had a probability mass function, the distribution, all right, so let's say that we have, 1 to 100 candidates, and somehow if we could sort of, let's say this was the distribution, and we knew that a lot of the initial candidates are really good, and the subsequent candidates are not very good, then we could use that distribution to be able to come up with a better estimate, okay? And yeah, that could be one way, but we don't really know what the distribution is, because the agency is, giving us, we don't have a lot of experience with them. We are assuming that they're going to be random, right? In other words, the probability mass function, the distribution is going to be fairly uniform. All right, so if there are 100 students, 100 candidates, then the probability that any one of them is better than the other is going to be, somewhat fairly uniformly distributed. That's our assumption. But again, as I said, the agency could be, making out for a buck, and they're actually giving you something like this. Okay, all the good candidates coming at the end. And if it's a really, that's a bad agency, and here's a good agency, which is giving us all the good candidates at the beginning. Okay, but we're now trying to convert this into a randomized problem. Okay, so I'm emphasizing that. Yes. Okay, So we could make that assumption, all right? So all of you have good thoughts, but I guess I'm not trying to, haven't been successful in trying to make you understand what I'm trying to say, which is essentially what I'm trying to say is I'm trying to convert this into a randomized problem, okay? So essentially what we could do, yes, one more time. So you could independently just do the hiring yourself? Sorry, is that what you're saying? Yeah, okay. So now you're getting at what we're trying to get at is that in order to convert this into a randomized problem, what you do is you take that input, you take all of the candidates, essentially you're saying that, okay, you've got all the candidates, but just give them all to me, all to us, the company, and we're going to randomize them. We're going to sort of make sure that all of these candidates are now randomly distributed. Okay, that you know, none of the initial candidates are good, none of the initial candidates are bad. We're just going to make sure that they're all random. And then we're going, and that's called randomizing, converting into a randomized problem. Okay, so think about, and we're going to stop for a few minutes, in a few minutes. So think about any sorting algorithm. Now, when you've been given a bunch of numbers to sort, a lot of times what happens is that there is an inherent distribution in that sequence. Okay. Now, randomized algorithms, what they say is that we're not going to take that sequence as it is before we apply our algorithm. What we're going to do is randomize that sequence before we apply our algorithm. Okay, so it's a different way of approaching the problem. You simply have an early step which says, I'm going to take the candidates, all of them together. I'm going to randomize them and apply the same strategy as earlier. Okay, so that's called randomized problems. And you'll see a whole class of problems which simply take the input, randomize it, and then try to work with it, just like the old problem. Okay, so you can convert any one of the sorting algorithms into a randomized sorting algorithm. Okay, all you need to do is have an initial step which simply randomizes all the sequence of data. Okay, so let's stop over here and we'll continue and take a look at this problem in the next lecture.